All right, good afternoon, everyone, and thank you so much for attending our monthly College of Natural Sciences webinar. My name is Allison Sherwood. I'm the Associate Dean for the College of Natural Sciences. And through this Pilina webinar series, we're aiming to reach the broader community and share the world-class research that happens within the College of Natural Sciences and across the Manoa campus. Today's presentation features Dr. Karen Meech from the Institute for Astronomy. Dr. Meech is an astronomer, astrobiologist who investigates how habitable worlds form, exploring the bigger picture of whether there is life elsewhere. Her work has embraced the power of interdisciplinary science, and she's combining geological fieldwork, geochemistry, astronomical observations, theory, and space mission concepts to address fundamental questions about how Earth got its water. She began her career in physics and astronomy with an undergraduate degree in space physics from Rice University and a PhD in planetary physics from MIT, after which she joined the faculty at the University of Hawaii. She served as graduate chair and the interim director for the Institute for Astronomy. She has won many awards for her work, including most recently the Danny Heinemann Prize. She was co-investigator on 3 comet missions, Deep Impact, Epoxy, and Stardust Next. She's been leading the development of a space mission to study icy material in the asteroid belt and led the team to characterize the first interstellar object that was discovered passing through our solar system. And so now I'd like to turn over our time to Dr. Karen Meech for her talk entitled What We've Learned from Our First 2 Interstellar Visitors. Welcome, Karen.
Thank you very much. Let me share something, get it all set up. And I will turn on the little laser pointer because it'll be easier to see things. All right, so thank you for the introduction. So let me start with the discovery of our first interstellar visitor. It was discovered with the Pan-STARRS telescope. Here's a nice image of Pan-STARRS, which is over on the island of Maui. Now, Pan-STARRS is a survey telescope that tries to survey as much of the sky as possible. And right now it's being funded to look for potentially hazardous near-Earth objects. So these are things that come very close to the Earth, and if they come too close, could potentially impact the Earth. So it scans the sky every night, and then Pan-STARRS staff looks at the data the next morning. So this is what the whole detector array looks like. It's huge. In fact, there's 60 devices. Each one of these is divided up into 64 subarrays. So on the night of October 19th, 2017, Pan-STARRS imaged a faint moving object, and the staff member on duty at the time, Rob Warrick, noticed this and noted it and said, all right, we've got something that's close to the Earth moving rapidly, so near Earth object. Now, normally the Pan-STARRS system works by taking a series of images and then it automatically flags things that are moving. But because there's a lot of defects on the device, a human has to look at these each morning. So Rob looked at the data from the night before, and it was actually there, but the system hadn't flagged it because there weren't enough images. So now they have 2 nights, which starts to give you an idea of what the orbit is like, but it's not enough for a good orbit. So right after that, people started to follow it up who were working with the Pan-STARRS team. Marco Michelli, shown here in the background, followed it up in Europe. And then Richard Wainscoat, who's the PI on the program, used the 3.6 meter telescope on Mauna Kea here to get a really nice image, and that's shown here. So this was on the 22nd of October, which was a Sunday. Now, I had just come back from a big science meeting, the premier one in astronomy for planetary scientists. I'd come back late on Saturday, and I'd been working fiendishly for about a month, and I thought, you know what, Sunday, I'm just going to do absolutely nothing. It's my day off to finally relax. Well, Richard calls me at home and said, I think we have found an interstellar object. And what that means was they finally had enough data to get the orbit. Anything that's in a circular orbit around the sun has an eccentricity of 0. If it's almost 1, it's a really elongated elliptical orbit. If it's greater than 1, it's coming from outside. And I was silent for a minute. My first thought was, did it really have to be today? This is my day off. But then I got excited and I thought, wow, this is pretty neat. And so I knew this was going to mean a lot of work. So in fact, it wasn't announced to the world until a couple days later. The formal orbit was published, and then it got a designation that Minor Planet Center uses. So this was asteroidal. It didn't have any apparent comet tail. The year 2017, and it was U1 instead of the survey catalog name. So where did this come from? Well, it came from above the plane of the solar system. So here's the orbits of the planets. It came beneath the sun, and then it had already passed Earth when it was discovered. So here's a blow up of that central region. So it came beneath the sun, inside the orbit of Mercury. Here's where the Earth is in its orbit, and it was discovered when it had just passed Earth. And so in fact, people said, well, couldn't you have found it sooner? And in fact, the answer is maybe on the 14th, but any sooner than that, you can tell if it's in here, you'd have to be pointing your telescopes towards the sun, and you don't do that. We could have found it when it was a lot farther from the sun, when it was above the plane, say over in here, but it turns out it would have been way too faint. So in fact, a lot of people ask, well, where is it now? Is it long gone? Well, we can certainly never observe it again. So the story I'm going to tell you is about what we could do in a very short period of time, but it's going to be inside our solar system for a long time. So for example, in June of 2022, it was at 30 AU, which is about the orbital distance of Neptune. Next February, it'll be at about the orbital distance of Pluto. It won't have even left our solar system by the year 2200. So it's going to be around a while, but we'll never see it again. Now, these catalog names aren't very sexy. So in fact, we knew it was the first of its kind that had ever been observed in our solar system. We wanted a real name. So within a few days of discovery, we approached 2 specialists in the Hawaiian language to ask them to propose a name, since it was discovered in Hawaii. And Larry Kimura and Kiao Kimura proposed within a couple days the name Oumuamua, meaning scout or messenger sent from our distant past to reach out to us and build connections. So we actually got that name proposed to the International Astronomical Union, and in lightning speed. Now, usually this is the main body of astronomers that makes formal decisions on names in the solar system. And it usually takes years to make a decision, but they realized this was important to get out fast. And within a week, they'd said yes to the name. All right, so it's the first of its kind we've ever seen. What do we want to know about it? Well, everything, but it's a matter of what can we do. So we really want to know, what is it? We suspected it's a comet or an asteroid because we've been predicting these things for a long time. So you want the basics. How big is it? What's its shape? How massive is it? What's its density? How fast does it rotate? Because all small bodies rotate. And of course, what is it made of? Can we get the surface composition? Is it cometary or asteroidal? Can we get some chemistry and even detailed chemistry to really understand how it relates to solar system formation? And of course, the burning question, where does it come from? Well, there's a problem with all of this. This is showing a graph of brightness versus time. So here's the dates across the bottom in 2017. This is the astronomer's magnitude scale, where a factor of 5 magnitudes is 100, a change of 100 in brightness. So it was discovered here. This was the night before when we found the observation. This is when Richard and Rob realized it's an interstellar object. Of course, we have to get telescope time. So the effective time to do observations easily was a 1-week window after discovery. And then you can do more challenging observations for a couple of months. So let me explain how you normally get telescope time. You normally get an opportunity to request telescope time on big telescopes twice a year. You write a very carefully written proposal. They take a couple of months to review it. And if you're lucky, you might get one night or several hours worth of time on a big telescope. We have to compress all that time into about a day. So here's what happened. The Discovery my giving up my free day, realizing what this thing is. By Monday, we'd written a proposal and had it approved on the largest telescope in the Southern Hemisphere. We'd written a proposal to another 8-meter telescope in the North. And if you look across here, we can see proposals approved. We can see more submitted. These little stars mean we're starting to collect data on the object. So we collected data for 4 nights. And then it became too faint to do anything. So this is the time period when all the activity was happening. We got the name from our Hawaiian colleagues here. And during this week, all the team was working 24/7, and we were reducing the data and writing the paper and submitted it on the following Tuesday. And then, of course, at this point, I had to travel. I had another meeting in India, so I probably left on the 1st or 2nd, get to India on the 5th. We get the report back from Nature and are frantically revising the paper, resubmit it, and then it's in production by the end of the week. So this is the whirlwind idea of what happened to this one object. So what sort of telescope time did we get? Well, we pretty much tried to gobble up everything big on the surface of the planet. This represents all the teams that got data. It was about 12 teams, 15 large telescopes, including 2 in space. And altogether, it was about 100 hours of telescope time that was dedicated within 1 week. And I was even asking and approaching people that I didn't even know, saying, "Hi, we discovered X. Would you like to give us your telescope time?" And they were saying yes. So everyone was very collaborative. So what do we measure? Well, the very easiest thing is to measure the brightness. You can just take a detector, a camera, and get an estimate of the brightness. But what does that tell you? We can get at the size from the brightness, but we don't know if it's something small, like a firefly nearby, or if it's something really distant and large. So it depends on the size and distance, but it also depends on how reflective it is, because asteroids and comets aren't typically shining by their own light. So in fact, it could be a really large dark object or a really small bright object and reflect the same amount of light. What we do know is all comets that we've ever observed are really dark. They only reflect about 4% of the light. So on that assumption, we could estimate the size from its brightness, and it wasn't very big, only about 100 meters in average radius. What about, is it an asteroid or a comet? Well, an asteroid just looks like a point of light in an image, but a comet has a big, beautiful tail. So we took a lot of our data and added it together. And the important part to look on here are these 3 images. These are 3 nights with a big telescope, all of the data stacked together. It just looks like a point of light, no obvious tail. Down in the bottom panel, these 2 are simulated images with a solid body and a tail. This one, you take 200 kilograms of dust and spread it out. This one, you take 2 kilograms of dust, or about a 5-pound bag of flour, spread it out over 1,000 kilometers, and that's how it would look in the simulation. And then we use several different techniques to try and magnify the faint light. And you can see for a tiny little bit of dust, you can really easily see it. And for all of the real data, there's absolutely nothing. So we declared there is absolutely no dust around this thing. It looks like an asteroid. So the next bit is composition. What is this thing made of? Well, in fact, the way you really want to get at this is spectroscopy, where you spread the light into its component colors. But it really was too faint to do that. To do spectroscopy, well, you want to be above this, and you can see we didn't have much time to do this. So colors gives you sort of the poor man's spectroscopy. And so this is a measure of the colors from the blue out to the infrared. And you can see as we go redder and redder, it's getting brighter and brighter. So what this means was it's red. Well, a lot of things are red. And in fact, Mars is red. And that's because of all the iron in the minerals on the surface. These straight dashed lines here represent comet surfaces. Comets are red for a different reason. They're covered in organics. Here's some other solar system bodies. Pluto is red because of the organics. This icy moon of Saturn is actually quite red, and I'll show a picture of that one. And then another asteroid, which is metallic, is red. So color alone doesn't give you much composition. So here's some actual images. Here's the comet 67P that was visited by the Rosetta spacecraft, a black and white image. You can see the solid body with the gas and dust coming off. Here's a close-up. And this is what red looks like on a solar system body. It kind of looks brownish. Here is that strange moon Iapetus. One side looks quite red. The other side looks bright and icy. And it turns out that this is an icy body that's moving through dusty debris in its orbit. So the front side looks red. Here's what Oumuamua would look like if we'd taken a color photograph, just a point of light that's reddish. Now, a lot of people criticized us for not getting HST data immediately. When you ask for Hubble Space Telescope data, this is a precious asset, they upload the commands to take astronomers' images about every 3 weeks. And if you want it right now, you can, but it interrupts all of those observations and you lose a lot of telescope time. So people said, well, why didn't you interrupt the observations? I said, well, we were going to get a point of light. I didn't see any purpose in disrupting the entire schedule to get a point of light. So we actually had a different experiment in mind with our Hubble Space Telescope observations, and that was to get images as long as possible as it got fainter and fainter so we could figure out where it came from. So the next thing that we wanted to do to characterize it is how fast is it rotating? Because everything in space spins. So this set of images here, and it may have a slight delay because of Zoom, is a series of images taken by Richard Wainscoat on Mauna Kea, and Oumuamua is in the center yellow dot. And you'll notice that bright stripe that went through is a meteor. It's getting brighter and brighter. All of these streaks that are moving along are the stars. So the telescope is moving at the speed of Oumuamua. And you can see it's getting brighter and brighter. Occasionally it passes over the field stars. Now, if we were to plot the brightness as a function of time, you can see it's going up and down. And in fact, on the scale over here, it's changing in brightness by more than a factor of 10. And what that's related to is as a comet rotates, the sunlight, or an asteroid, the sunlight is reflected off of the different sides. And if it's reflected off of a large area, it's bright. If it's reflected off of a small area, it's faint, and so forth. All right, so how fast is it rotating? Well, people had some estimates. Some people had just a little bit of data. They said, well, it's longer than 5 hours. Maybe it's near 8 hours. But once people started to get good data, they tried to combine it all and fit a single period for its rotation. And no matter what you picked, it looked like a mess. All of the data doesn't line up on each other. What's going on? Well, it turns out it's not a simple rotation. It's actually rotating around the short axis, and it's oscillating this way, and it's wobbling up and down. So in other words, it's like a top that you're spinning that's wobbling. So how does that happen? Well, there's a couple of ways it can happen. That we see this happen with comets all the time. Comets don't just release their gases uniformly. It often comes off in jets. And those act like little rocket thrusters that can speed up the spin. And so you can get the wobble. This is again that comet that was visited by the Europeans. This is another comet. We can't actually see the comet, but what you can see is the result of the jet spewing out dust and gas and the comet rotating. So it's acting like a sprinkler on your lawn. And so you can see the rotation in the dust and gas. That's one way it could have this strange rotation. Another way, since we think this is a fragment of the planet building process in another solar system, maybe when it was kicked out of its home solar system, somehow it passed really close to a giant planet and it caused it to tumble effectively. So we have an idea that it's rotating around this short axis at about 8.7 hours. But we can also get something about the shape by looking at the light curve. So in fact, if the brightness changes by a ratio of 10 to 1, then the naive assumption is, oh my gosh, the axis ratio is 10 to 1. This is really long and narrow. But in fact, what everyone neglected at first was to consider we're not looking at it face on. So if there's a shadowed portion of it, when you're looking at it at an angle, the lit portion looks longer and narrower than it really is. So maybe it's not 10 to 1, maybe it's a little bit fatter, it's 6 to 1, but it's still pretty bizarre. We've never seen anything in the solar system like this. And this is an artist's rendition of another potential shape that could give that same light curve. Of course, he's taken a lot of leeway with craters and it's way too red. In fact, this is one of the most enduring mysteries of Oumuamua, is what caused this strange shape. And there's been no shortage of papers. I mean, altogether, there's been a couple hundred papers written on 1 week's worth of data from this object. So there's all sorts of exotic ideas. I won't go through all of them. One idea was maybe in its home solar system, it passed really close to Jupiter. And as we've seen in our solar system, when comet Shoemaker-Levy 9 passed close to Jupiter, it got ripped apart. Maybe Oumuamua passed close to a giant planet and it didn't get ripped apart, but it got stretched. Maybe its home system went supernova, and so some of the ices got vaporized, and so it was left with an elongated remnant. Other people said, well, maybe it's made out of some exotic material, maybe it's a hydrogen iceberg, and as it comes into the solar system, and the reason I picked hydrogen is that's a gas we would not be able to detect. So maybe it was outgassing, and much like a bar of soap in your shower, if you remove a layer uniformly on the surface, it gets longer and narrower. So we don't know why it has this strange shape, and there's still people writing papers about it. So the big thing that we did with our Hubble Space Telescope observations was we wanted to figure out where this thing came from. So the idea was we had a lot of ground-based data, 177 different data points that very carefully measured the position of this object. And the idea is if you've got a long enough path and you carefully measure the position, you can go backwards in time and figure out where it came from. So the Hubble Space Telescope observations were to extend this by 2 months because it was too faint to get from the ground. Well, our dynamical colleagues fit an orbit to this and said, okay, let's subtract that fit and look at the leftover residuals. And if it's a good fit, these should be 0. So this is plotting effectively the latitude and longitude if you were on a globe. And you can see the residuals are not 0 and they're not random. It looks like there's some sort of pattern going on. So they said, okay, there's something else affecting the orbit. What if we consider a push or non-gravitational forces? So they did that, subtract the fit, and now you get what they expected to see with residuals. So in effect, what they found out, and this was Marco Michele, Davide Farnacoccia at Jet Propulsion Laboratory, they found out that Oumuamua is accelerating away from us. It's going faster as it leaves. And it's going faster, dropping off as the square of the distance. But we see this all the time with comets because they're outgassing. And the uneven outgassing often acts like a little rocket thruster. All right, we've got a great orbit now. Let's trace it to its home system. Well, this was only possible coincidentally during that year because a new catalog was just released. There'd been a European satellite in orbit making very precise measurements of the positions of stars. And not only positions, but positions over time. So they were getting velocities. Remember, everything in space is moving. So in order to trace its path home, we have to take account of the movement of the stars. So taking account of this, we trace backwards, and then my colleague was checking which stars did it come close to. And the question is, how close do you have to come? Well, this is a graphic rendition of our solar system, the sun in the middle, the planets, you can't really see their orbits. This is the Kuiper belt out beyond Pluto. And this is a vast cloud of comets that's called the Oort cloud. That's about 100,000 times the Earth-Sun distance, a big spherical shell, leftovers from planet formation. So we figured it has to pass at least within an Oort cloud radius of its home system, or it can't have come from that star system. So in these units, astronomical units of parsecs, it has to come to about a half a Oort cloud radius. So my colleague found 4 candidates, and he initially called them home 1, 2, 3, and 4. These were the distances at which Oumuamua passed those stars. This is the velocity. Now, how fast can Oumuamua have passed a star system and us consider it comes from there? Well, the only way it gets out of its home is likely it passed close to a giant planet and got kicked out. The velocities can't be very high for that, on the order of 5, maybe 10 kilometers a second. So what you're looking for is less than half and less than 10. And although these looked promising, none of them were good enough. So we determined you can't find the home for Oumuamua. In fact, it's probably impossible to ever find the home. And here's why. This is a movie that was made out of the release of 40,000 stars that were in our neighborhood, following their paths over 1.6 million years. And hopefully this will work in Zoom because there's going to be a latency delay. So here you can see the movement of the stars. Some of them make really long streaks, some are short. So everything is moving relative to each other. And now we're trying to trace the path of Oumuamua through this mess to figure out which ones it passed nearest to. And in fact, the errors get bigger and bigger and bigger the farther back in time you go. So probably most scientists have decided we can never do this experiment. It's probably too difficult. Let's come back to this acceleration. What are the possibilities? Well, as we mentioned, we think it's outgassing. This was behaving like a comet. It's got gas coming off, and that's creating an acceleration. Well, there's a problem with that. Normally, when comets spew off gas, they push dust off, and we certainly saw no dust. The Spitzer infrared telescope looked at Oumuamua, but they had to look at it in late November. And the reason for that was they can't point their telescope at all close to the sun. So they had to wait till it had moved away when it was really too faint for Spitzer. So this is the actual image from Spitzer. There's nothing here, but this is just noise in the sky. But from a non-detection, they said, well, we don't see any gas to a certain limit. So no gas or dust. So that makes it a little bit of a problem for it to be outgassing. Many other possible explanations, and I'm not going to go through this in detail, but the basic gist of these is there's something wrong with everything. For example, sunlight can exert a pressure on materials in the solar system, but the only way it could plausibly exert enough pressure to create the acceleration we saw is if this had an unreasonably low density, effectively less dense than styrofoam. And nothing natural has a density like that. Most of these others, the acceleration was in the wrong direction or way too high. So in fact, that left the only plausible explanation was that it really was acting like a comet. Of course, everyone says, I'm not too worried about the lack of detecting gas. We really didn't have the right experiment to do that. But we did have a very sensitive experiment to detect dust. So why was there no dust? Well, here's some beautiful images of recent visits to asteroids by spacecraft in our solar system. And they're all a similar size to Oumuamua, which was about 100 meters in radius. And what you can see is none of these guys have any dust either. They all seem to be covered in big boulders. And this is in part because when there's collisions, the fine dust settles in between the rocks. Or there were suggestions that if Oumuamua ever passed through a cloud of gas and dust on the way to Earth, that would have eroded the surface dust. So having no dust is not an unreasonable circumstance. So why was this so exciting? Well, what's really neat about Oumuamua This is a view of what our solar system may have looked like early in its history, just as the giant planets were forming, as the little building blocks are starting to either coalesce to become planets, or they pass close enough to the giants, they get kicked out. So Oumuamua may be a piece of this process from some other star system. Now, very interestingly, that same year, 2017, prior to its discovery, a paper came out by Tony Engelhardt, Rob Jedicke at IFA, and others, where they had made a prediction of how many interstellar objects like Oumuamua there should be, based on the fact there'd been an accumulated 19 years worth of all sky surveys and nothing had been detected. And so they made predictions. And the very fact that Oumuamua, which is the hardest one to see because it has no tail, it doesn't get very bright, was found first, suggests maybe there's a lot of these things in our solar system that we just don't see. And this is just showing a three-dimensional view of our solar system. AU is Earth-Sun distance. And so only the ones that would get really close to Earth would have a chance of being seen, but a lot of these could be whizzing through and we'd never know it. So astronomers were excited. The public was excited, and it actually made the front page of the Star Advertiser. So what was the next one? In fact, and I'm not going to go through as much detail on the next one, the second interstellar object was actually discovered a lot sooner than we expected. So the second one, which is called Borisov, was discovered by an amateur astronomer, Gennady Borisov, in August of 2019. And he was doing what the professionals could not. He was using his homemade small telescopes, and he was pointing in twilight with the sky pretty bright, really close to the horizon. And big telescopes don't usually do that because you want to use them to go after faint things when the sky's dark. This one was totally different from Oumuamua. Here's the Discovery image, and you can already see a little faint wispy tail. This had not yet made its closest approach to the sun. And unlike Oumuamua, it didn't come very close to the Earth at all. Its orbit stayed outside the orbit of Mars. So what do we know about this one? Well, it turns out that it was red, just like Oumuamua. It was also very small. Remember, Oumuamua is about 100 meters in radius, and this, we didn't have a very good estimate because it had a lot of gas and dust around it. But the very first spectrum saw that it does show gas coming off, and this shows cyanide coming off of Borisov. So it looks like a comet, although the chemistry is different from comets in our solar system. And then Hubble Space Telescope images showed that it fragmented, broke into two pieces in March of 2020. And again, in July, you can see a faint piece and a brighter piece. So the two interstellar objects were just as different as they could be, with one exception. Remember, I'd said the first one was right when I'd finished this Division for Planetary Sciences meeting. Well, in 2019, the same meeting was meeting with the Europeans in September. And so the second one was discovered in August. It was decided that it really was an interstellar object on the 9th of September. And then everyone's flying to Switzerland to go to the same meeting. And so you're busy, instead of getting ready for traveling, you're writing proposals for telescopes. Everyone's scrambling at the meeting. That's all people were talking about. Right after this meeting, there was another meeting in Switzerland just to talk about interstellar objects. So I think the moral is these things are always going to be discovered when you're absolutely the busiest or when there's one of these annual meetings. And in fact, during that week, because there were other things going on, I was working on some mission proposals also. I noted to a colleague, I said, each of those 2 weeks were about 120-hour work weeks. And he said, I didn't know there were that many hours in a week. Are those dog hours? So what's the legacy of these things? Well, you know, it really is a rare opportunity to study a sample from another solar system. We're never going to get this opportunity to study something this close from another star system. We want to know, do planets form the same way everywhere? Is the chemistry the same? You know, I think some of the answers for the next interstellar object may in fact require a space mission. And for the last bit of the talk, I want to talk a little bit about space missions. But, you know, we have to come back to why a lot of these surveys are scanning the sky, and that's to look for things that come close to Earth. Now, most people don't realize that Oumuamua got really close to the Earth. It came within 63 Earth-Moon distances, and we didn't know it until after it had passed by. It was moving fast. So this is at perihelion, its closest approach to the sun. It was moving 68 kilometers a second with respect to the Earth. And since most people don't think in kilometers per second, that's about 153,000 miles per hour. That's a lot of energy. When it passed closest to Earth on October 14th, it was going a little slower, but that's still 134,000 miles an hour. And if you take an estimate of the mass of this thing, this is about 14,000 megatons of TNT. So this is about 1 million times more energy than the Hiroshima explosion. This wouldn't be extinction level, but it would be regional destruction. So 63 Earth-Moon distances is pretty close. So what if we'd had a 30-meter telescope, either the extremely large telescope being built in Chile by the Europeans, 39 meters, or TMT on Mauna Kea? What could it have done for Oumuamua? Well, it could have seen in part of the night how big it is, how dark it is. We could have gotten gas. We could have done detailed measurements of the gas and really have a firm understanding if other solar systems are different. And in fact, we may soon be flooded with these things. The new Rubin telescope should be commissioned next year in Chile. And predictions are that it may find one interstellar object per year. And now you're going to have all the astronomers scrambling to get telescope time, and it will be a frenzy all the time for astronomy, a good frenzy. So let me finish off with missions. If what you really want is detailed science, one way to do it is to get up close, and that's with a mission. So once in a lifetime missions really need a fast reactive mission. You saw Oumuamua, it was here for such a short period. Now, the way NASA and the Europeans work typically is it's like a 10-year horizon. They put out a call for proposals. People propose a mission. For example, right now there's going to be a call next year for the billion-dollar class missions with launch window availability between 2031 and 2034. So 8-year lead time or so. Well, these guys have to be reactive. There's also a lot of challenges to these missions. One of these is these guys, whether it's interstellar object or coming from our own Oort cloud, which we've never looked at up close, they come in fast from any direction. And if you're trying to do a mission that's not in the plane of the solar system, it takes a lot more energy. Secondly, when you're going this fast, any dusty debris near the comet is a big hazard. For example, this was an actual image from the epoxy mission, which went to Comet Hartley. And all of these dots here are not, in fact, stars. They're, we'll call them dust grains, but they were centimeter to 10 centimeter scale grains. You smack into something like that at these speeds, and that's going to be catastrophic. In fact, with the Giotto European mission flying through Comet Halley's tail, it was destabilized by a 1 gram grain of material. Finally, what you'd really like is a rendezvous. That means you slow down, you match the speed, you spend a lot of time at the comet. We probably can't do that with these missions, and here's why. This was prepared by a colleague at JPL. This is showing effectively how much velocity you have to give the spacecraft at launch. Think of it as cost. Think of this as money. This one is how fast you fly past it. What you really want is 0. That's a rendezvous. You stay there, you look at it. Well, the colors on here show the probability or the percentage of new targets that we could hope to have a mission to. This deep blue color is 0. So no matter how much money you spend, we probably don't have enough energy to get to one of these and have a rendezvous. If you're willing to spend a lot of money and are willing to go to really high flyby velocities, maybe 55% of these are reachable. So these are going to be really challenging. So we want a rendezvous, we can't get what we want. Maybe the thing to do is have your fast flyby, but have a spacecraft that spits out smaller pieces. So everybody has their own job. Small things can go in really close where it's hazardous and relay their data back to the parent spacecraft. So in fact, the Europeans have a mission called Comet Interceptor, which is designed to do this. It doesn't quite have as many pieces. It's got 5. So it was selected and they're now working through their design reviews. The intent is to launch it from Earth in about 2029 and just hover near Earth and wait for up to 6 years until an appropriate comet comes along that meets the right criteria, and then head over to the comet. So you've got to have something built and waiting to go. And of course, they're hoping for an interstellar object, but I think the chances of that are really small. So just for a moment, before we finish up, I'd like to get back to the cause of acceleration. Remember, everything was ruled out except the top one. And I spent a little bit of time talking about this idea of radiation pressure, that sunlight can push something. We ruled this out because it was impossible. There's no natural thing that has densities as low as styrofoam. Well, I'd like to talk a little bit about science ethics, or lack thereof. There's one scientist at Harvard who claims that clearly Oumuamua was not natural, but it was in fact an alien spacecraft, and that the radiation pressure explanation matches. And so he's claiming it was a solar sail. The sun's radiation pressure pushed the sail, and that's why it was accelerating. Well, there's a lot of problems with this hypothesis. First of all, I don't know how many of you are sailors. I'm not a big sailor, but usually you point the sail in a certain direction so it catches the wind. You can't have your thing tumbling erratically and hope to have it catching the wind and being accelerated. Another thing that Avi Loeb had proposed was that it couldn't possibly be a natural object because it was too reflective to be natural. Well, if you remember from this previous slide, there was no detection at infrared wavelengths. We did not measure its reflectivity. The team that did this measurement said, as an upper bound, it might be around 20% reflective, which is about the same as the lunar Maria on the moon. So that's within the bounds of natural solar system objects. So apparently he doesn't understand the reflectivity of solar system objects. And so what he's done is he's cherry-picked some of the specific details that fit his hypothesis and ignore the rest. He's written books claiming that this is the first interstellar technological evidence of life elsewhere that's visited our solar system, and he's been getting movie offers and so forth. And was chair of the Harvard astronomy department and so forth. You know, as our friend Carl Sagan would say, extraordinary claims require extraordinary proof, and Avi Loeb has no proof whatsoever. So, you know, it's a little bit sad because it teaches our students in science that this is the way to do science. Dream up a hypothesis, pick the bits of data that fit, ignore everything else, and you've got your answer. But there has been some fun with this. Because of this discovery, I was invited to give a TED Talk. And like a true scientist, well, here's an image of me giving the talk. It was one of the most nerve-wracking things I've ever done. This is what the TED stage looks like in Vancouver. You notice there's all these beautiful blue sofas. That's where the people that paid the highest price for the ticket sit, and then the cheaper seats are out here. And you have nothing between you and the audience. And so you're just talking for 13 or 14 minutes. So like a true scientist, I've been charting how many views are on the TED Talk. And notice here, when Avi Loeb's paper came out claiming it's aliens, there was a huge uptick on the talk and so forth. And as of a few days ago, it's up to quite a few views. One nice thing that happened that's not scientific, and I wish I'd known this at the time I gave the TED Talk, because apparently this was manufactured at a brewery in Vancouver, was the Oumuamua milk stout. And on the back of the bottle, it says forever caressed by blackest space, the hurtling megalith returns, Earthling's prodigal creator in a dense velvet-wrapped disguise. Its secret pilots seek adulation, sweet desolation, eternal cold burn. Sapiens myths rewritten to reveal the cosmic truth inside. So this was driftwoodbeer.com. I don't know if they still make it. I've got a bottle of it. I've not opened it, but apparently stouts don't keep forever, so I should drink it at some point. So with that, there's been some fun, there's been some ethics issues, and there's been a lot of cool science with the interstellar objects. And the next DPS meeting is in October, so that's probably when we'll have the next one. Although there is a big science meeting for comets and asteroids and meteor people in June. So with that, are there any questions?
Thank you so much, Karen. That was a wonderful talk. I really enjoyed your presentation today. We will open up for questions now. So any of you, feel free to unmute your microphones or put questions in the chat box. I'll start us off then. So I'm wondering if you can tell us a little bit more about the process that was used to come up with the Hawaiian name.
Well, Doug Simons, our director, had been working, and I don't know the history of this, now they've got a formal process to come up with names, but I think it's a really nice mechanism to recognize discoveries that are made in Hawaii, to involve the Hawaiian culture and get the local culture to come up with a meaningful name for each of the new objects. And I did notice that Doug is on the line if he wanted to say something more about this, but I think this was before it had become a formal process. This was sort of an opportunity to test it.
Thanks very much, Karen. Does anyone else have questions? Yes, go ahead.
Hi, Karen.
Hi.
I understand that it's too hot or chancy that we'll have an spacecraft actually watching for it. But if one of these will come by in the future, are there more plans on how to observe it?
Well, the next one that comes around, you can be certain there's going to be a huge frenzy of everybody to get telescope time. Many astronomers every semester now put in proposals called target of opportunity to say, if one comes along, I'd like that time already allocated. And our team actually got a target of opportunity proposal accepted for the James Webb Telescope. In terms of a mission, there just really is no chance because, for a space mission, unless it's ready and waiting to launch to something, the cameras on most missions are not designed to look in a distance. They're designed to look at something up close. So even if something was discovered and you've got a mission en route to somewhere, the chances that it could look at it are very small. This Comet Interceptor mission from the Europeans is really a nice experiment. And many scientists have written to NASA saying NASA needs to develop a mission style that is responsive because there may be other things that are equally exciting that you have to go to immediately.
I would ask, for a comet, it might be easier because is it true that you probably can spot it a bit earlier, and so you can actually follow its trajectory or orbit or something. Unlike this thing, it's just kind of appear and you discover it afterwards.
Well, Pan-STARRS, for example, in Hawaii has been very good at detecting comets while they're very far from the sun. And so you may get 10 years of warning, and then it would fit within the classic paradigm for missions from NASA. But the problem is whether or not you can get to it, and all of these things tend to come from above the plane of the solar system. They're much more likely, this is how out of the plane it's coming. And they can come from any direction. And that takes a lot more energy with the spacecraft. If it's in the plane of the solar system, it's much easier. So I still think it's a challenge for NASA.
Okay, thank you.
We have a couple of questions in the chat. The first one's from Maria. Are object rotations all the same direction, or are they just random?
For these small bodies, it's probably random. The planets tend to rotate in the same direction because, you know, they're coming from, you know, you can look at sort of the background. Oh, no, this image is better. They're coming in the solar system. The whole disk of gas and dust is rotating slowly, and as things come together and coalesce, they maintain that angular momentum or that rotation. Comets can rotate differently because they're outgassing, and that exerts some forces. You know, some of our bodies in the solar system rotate backwards, but there's interesting explanations for those. So small bodies can rotate in any direction. And then, of course, if they're outgassing, they can change their rotation rate.
Okay, and so related, well, sort of related to that, the next question in the chat from Ado is, what are the chances that it was outgassing hydrogen?
Well, the reason for these two exotic hypotheses was because we could not have detected those gases spectroscopically. They don't have any means of detecting them. And so they said, all right, let's make it have an outgassing that's really strong that we can't see, and that's why we didn't see it. Well, the problem with the hydrogen iceberg hypothesis, Daryl Seligman had proposed this, there really isn't a good mechanism for making it. Hydrogen is a gas that would freeze at absolutely the lowest temperature, and it would have to be in the coldest, darkest places in space. And most scientists just think you can't manufacture a hydrogen iceberg. Nitrogen will be a little bit easier. Steve Desch said, well, what if it's like a chip off of something like Pluto, which has nitrogen ice all over the surface? But people also don't think that this was a very likely hypothesis. But what has been fascinating to me have been the wealth of really creative ideas, aside from alien technology, the creative science ideas to explain the shape of Oumuamua. We've got people coming from very different fields. We've got dynamicists, we've got people that study galaxies and stars, people that study exploding stars, trying to figure out what this thing was. We know the shape, sort of, and that's about it.
Okay, we have another question in the chat. Is the general scientific thought that as observations increase, more objects found will also have a 10 to 1 ratio or similar in the future, making the shape less rare?
That would be really interesting. You know, here we've discovered two. We've got one that looks really weird, elongated, inactive, and we've got one that looks like an ordinary comet, and we have no idea what the shape is. You know, I don't know that we'd even want to dare bet what the third one might be like. You know, the prediction was the easiest to discover will be the ones with tails because they get brighter. So if we get another one that has no tail and it's round, that still makes Oumuamua a mystery, and that means Avi Loeb will write even more textbooks on why it's an alien spacecraft. And, you know, just to be honest, our team, the day or two after discovery, when we were using the horrible name from the survey, which I've forgotten by now, but P10EE5V, I thought, I can't keep typing this. And so we speculated a bit, and we were thinking, well, we could call it Rama, as in rendezvous with Rama. And I'll have to admit, I even looked up the spectral reflectivity of titanium, i.e. a good metal for spacecraft, and it's red. But, you know, we very quickly were amused by that and then went on and did real science, unlike other people.
Okay, a couple more things that have come in through the chat. So first of all, are there any upgrades to existing equipment that will increase the possibilities of detecting these objects coming inbound?
Not so much equipment, but if you want to call a telescope equipment, this telescope, which has now been built and it will be commissioned and supposedly on taking data next year. This is in Chile. This is an 8-meter telescope, so it's much bigger than Pan-STARRS, and it's going to be surveying the whole sky. So it will be able to see much fainter objects. So this is a leap forward in terms of detecting faint things that are moving. So that's why the predictions are that it will discover maybe one a year that we're going to have to follow.
Okay.
Karen,
Yeah.
Sorry, go ahead, Mark.
can you tell from the light curve that all of this is due to geometry rather than reflectivity like iapetus?
Yes, and I just so happen to have a background slide on that. If it's the iapetus, which is here, if it's the reflectivity or albedo, as we call it, bright versus dark, that tends to give you a very even sinusoidal-like light curve. If it's due to shape, you tend to have these pointed V's at the bottom of the light curve. So if we go back and look at Oumuamua's light curve here, you can see it's got these pointed V's. So this is clearly a shape light curve. And anytime you see a comet nucleus that has this sort of bilobate shape, it tends to give you these sharp V's at the minimum brightness. So I've got chat open and I see another question. Since it wasn't detected until passing Earth orbit, does this show us that we're always in danger since we could be whacked without even knowing it? Well, yeah. And that's, in fact, the whole point of having surveys like Pan-STARRS. You know, it's funded mostly now by NASA to survey the sky every night. And I still think it was pretty scary that, you know, it had passed that close to Earth, 63 Earth-Moon distances. And this, if it had whacked us, we would have known it. I guess if you're going to get whacked, you'd rather not know it's coming and have everything destroyed, but this one would have just destroyed a region.
So on that note, that cheery note, I think we'll wrap up our Q&A session. Thank you, Karen. That was really a wonderful talk. I'm very grateful to you coming back and speaking to us once again for a really wonderful webinar. So thank you. And thanks all of you for attending today. We had a great audience today. We're going to be taking a couple of months off for summer break, but we do look forward to seeing everybody in the fall when we're back. And we're going to have an exciting new season of talks for the upcoming academic year. So watch your inboxes towards the end of the summer to receive notice of what we have lined up for the fall semester. And we hope to see you then. Have a wonderful rest of your day, your evening, and have a safe, happy, enjoyable summer. See you soon. Aloha.